Bismillahirrahmanirrahim. Assalamu alaikum. Hi viewers. Today we are going to start the part 2 for basics of pipe stress analysis. In part 1 we have discussed causes of stresses in piping system. We have discussed about type of forces acting on a pipe, type of stresses in a piping system, the concept of tensile and compressive forces and stresses, the concept of stress and strain in material, and the relationship between stress strain through stress strain diagram. Then we discussed the concept of different region in stress strain diagram like elastic region, plastic region, the concept of strain hardening. Then we discussed about how to calculate proof stress for a material having no specific yield point. Then we discussed difference between true stress strain curve and engineering stress strain curve, and the use of stress strain curve in engineering. In this part 2 we shall discuss about the type of stresses in a piping system in detail, so that before proceeding to formal stress analysis through Caesar software we should have strong understanding of different type of stresses, their calculations, their allowable values, and their root causes. It will help us to understand the stress analysis and to evaluate the Caesar software output results. So let's start to understand how to calculate different type of stresses, their allowable values with respect to code, their mode of failure in piping system. The first one is failure by yielding. In this mode of failure, material follows Hooke's law, and after elastic limit, yielding starts and material enters in plastic region. Causes of this kind of mode of failure could be either yielding at sub-elevated temperature or yielding at elevated temperature, which is called creep. Now, the second mode of failure is failure by fracture. It has further divided into sub two types. The first one is brittle fracture. Brittle fracture, such mode of failure happened mostly in brittle material which fracture suddenly without any pre-indication of failure. The second type of failure is fatigue failure. Fatigue failure in pipes are of mainly three types. Thermal fatigue failure, it is due to expansion and contraction in pipe because of change in temperature. Number 2, vibrational fatigue failure. It is due to vibration in the pipe due to some excitational force like slugging or vibration due to rotating equipment, etc. Then third type is static fatigue failure. It is due to sustained load. When a pipe sustained a high static load for a long time, it fails due to static fatigue. The third one is creep failure at high temperature, which is normally considered above 500 degrees centigrade. The material fails because of elevated temperature. Theory of failures. The failure theories most commonly used in piping designs are maximum principal stress theory and maximum shear stress theory, which is also known as Tresca criteria. What is maximum principal stress theory? This theory states that yielding in piping component occurs when the magnitude of any of three mutually perpendicular principal stresses exceeds the yield strength of the material. These stresses are sigma x, sigma y, or sigma z. Either of these, if it is more than the yield stress of the material will fail. This is the maximum principal stress theory. The second most commonly used theory is maximum shear stress theory. In maximum shear stress theory, it states that the failure of piping component occurs when the maximum shear stress exceeds the shear stress at yield point of the material. Let's assume sigma 1 is greater than sigma 2, which is greater than sigma 3. Then sigma 1 minus sigma 3 divided by 2 is equal to tau maximum. In tensile test, sigma 1 is equal to Sy, then sigma 2 is equal to sigma 3 is equal to 0. It means the yielding in the component occurs when sigma maximum minus sigma minimum divided by 2 is equal to tau maximum, which is the shear stress, or which is equal to yield stress divided by 2. It means 2 tau maximum is equal to sigma maximum minus sigma minimum is equal to yield stress of the material. This stress is called the equivalent intensity of the combined stresses or stress intensity. Hence, we can directly compare the stress intensity S with the yield stress of the material with the safety factor. The maximum shear stress theory forms the basis of piping systems governed by ASME B31.3 section 3 of ASME boiler and pressure vessel code. It means the maximum principal stress theory normally used to evaluate in piping stress analysis by the code ASME B31.3 and ASME boiler and pressure vessel code. Here, as you can see, the 2 tau is equal to sigma maximum minus sigma minimum, which is equal to yield stress of the material. Type of the stresses in piping system. The piping system experience total 10 types of stresses throughout its life. As you can see here, compressive, tensile, shear and bending stresses or torsional stresses in this picture. So let's discuss one by one. The first one is hoops or circumferential stress, which is indicated normally with SH. Second one is axial or longitudinal stress, which indicate with the symbol SL. Third, bending stress, which normally indicated with SB. And all these three stresses, hoop stress, axial stress and bending stress, are called the principal stresses, which we have studied during engineering in reference to Mohr circle as well. Shear stress normally indicated as tau or simple tau, and torsional stresses as T. And these two stresses, shear and torsional stresses, are not principal stresses. The radial stress indicated with SR. The radial stress is ignored in stress analysis for thin walled sections or cylindrical or pipes. In thin walled pipe, it is ignored. Normally we ignore radial stresses in stress analysis. We'll discuss all these types in details in further slides. Sustained stresses are due to the weight of the pipe, piping component, weight of the insulation, internal pressure, and due to this internal pressure, there are further three types of stresses developed in piping, which is hoop, axial, and radial. So sustained stresses are also called the primary stresses, and these are also known as non-self-limiting stresses. Occasional stresses. Occasional stresses are act occasionally on piping system like wind, earthquake, PSV reaction forces due to PSV pop-up, surge forces and slug forces. Main occasional stresses are also considered under primary stresses. Thermal stresses. Thermal stresses are due to temperature and are called secondary stresses, which are self-limiting in nature. The last one is fatigue stresses, are cyclic in nature and also comes under secondary stress category. So these are the 10 types of stresses that piping system has to face during its entire design life. So let's discuss one by one all these stresses, how to calculate these stresses, and what are the allowable values for these 10 type of stresses. When hoop stress will produce in piping system? So it's a question mark. So the circumferential stress, also known as the hoop stress. The stress that occurs in a pipe in circumferential direction, it causes by the internal pressure acting on the wall of the pipe. When we consider both ends of the pipe as closed end and then internal pressure of the pipe causes the force on wall of the pipe that produce hoop stress, which is actually in circumferential direction of the pipe, as you can see in the picture. Let's consider half section of the pipe having length L as shown in the picture, thickness T, and inside diameter Di to understand the concept of hoop stress and how to calculate the hoop stress. As we studied in part 1 about the stress is equal to applied force divided by the cross-sectional area. Means we need to consider the applied force acting on the pipe, which is pressure in our case right now, and area where this force will act, which is internal diameter of the pipe at the length L of the pipe. Hence, the force is equal to internal pressure applied at the area AP, which is inside diameter of the pipe. Now, AP is the inside diameter of the pipe multiplied with length of the pipe, which is L. So, area AP is equal to Di into L. Now, the force will be equal to F is equal to P into Di into L. This is equation number 2. Let's calculate the area that will fail due to the circumferential stress or the hoop stress is the longitudinal area of the pipe, which is highlighted in red in the picture, as you can see. This area shall experience the stresses that is trying to break the pipe into two halves. This area is called the longitudinal area of the pipe, which is equal to the total length of the pipe multiplied by the thickness of the pipe. 2T means two thicknesses, upper thickness and the lower thickness, when we'll cut the pipe into two halves. So here area is equal to L into 2T. Let's substitute these two values from equation number 2 and equation number 3 in equation number 1. We'll find the sigma H, which is circumferential or hoop stress, is equal to P into Di into L divided by 2T into L. So L will be crossed with the L. So balance is sigma H, which is equal to PDI over 2T. But commonly in our calculation we used outside diameter of the pipe. So sigma H is equal to PDO over 2T, because when we will calculate the stresses with internal diameter, it will give us less stress value. But if you will calculate the hoop stress with outside diameter, it will give us more conservative value as compared to inside diameter. That's why we consider outside diameter of the pipe in hoop stress calculation. To calculate the hoop stress, we normally used sigma H is equal to PDO over 2T, where sigma H is the circumferential hoop stress, P is the internal pressure of the pipe, D is the outside diameter of the pipe, and T is the thickness of the pipe wall. We can also calculate the hoop stress with another method, as we know that for equilibrium system, applied force on the pipe is equal to the resistive force of the pipe material. Means pressure multiplied by area AP, which is internal diameter of the pipe, multiplied by the area length. So AP is Di into L is equal to sigma H into A. Sigma H is the hoop stress which is produced at the area A. So let's calculate P into Di into L. P is the pressure, Di is inside diameter, L is the length. Sigma H is equal to the area, which is the highlighted in red color, L into 2T. In this way, sigma H is equal to PDI over 2T. Again, instead of Di, we'll use the outside diameter for a conservative value to calculate the hoop stress. Hence, the thickness formula of the pipe in ASME B31.3 is based on hoop stress formula, which is T is equal to PD over 2 sigma. Here P is internal pressure, D is the outside diameter, 2 into SEW. S is the stress, allowable stress, EW plus PY. P again is the pressure. So hence the thickness formula of pipe in SBB 31.3 is based on Hooke's stress formula, which is T is equal to PD over 2 sigma. That comes out like PDO over 2 SEW plus PY.